So now that I've given you a quick overview of the API that forms the basic portion of the completable futures, let's take a look at how you might actually apply these basic features to operate on big fractions. And we'll also talk about some of the limitations with this approach. So I think I mentioned this before, but a big fraction is a class that allows you to do arbitrary precision fractions. And the reason it allows arbitrary precision fractions is it has big integers for both the numerator and the denominator of the big fraction. And big integers are these arbitrary precision integer values. You can use various factory methods to create so-called reduced fractions. So a reduced fraction would be one where you give a numerator and denominator that can be reduced to a simpler form, as shown here. I'm sure you're all familiar with this from probably 7th grade or something like that, or earlier. You could also create non-reduced fractions and then later reduce them. So you can indicate whether you want a fraction to be reduced or not. And we'll talk about why you might do that in a minute. And then there's a bunch of obvious arithmetic operations to multiply and subtract and divide and add big fractions. So you can imagine stuff like this. You could multiply big fractions. And then the final set of things you can do here is you can create a so-called mixed fraction from a so-called improper fraction. So if you've got an improper fraction like this, then you can go ahead and create a so-called mixed fraction from that. OK, so that's basically what we're doing. Here's the way the code's going to work. You can see this in the EX8 folder in my GitHub repository. The right-hand side kind of shows what's happening from an interaction diagram point of view, and the left-hand side actually shows the code. So the first thing we're going to do is we're going to make ourselves a new completable future that's empty, so there's no computation associated with it at this point. We're then going to go ahead and make a new thread that's going to run in the background. That thread will perform this supplier lambda expression, where we're going to create two big fractions and multiply them together using the big integers in the background. So that'll run in a background thread. There will be some other computations, which we don't show here, that could go in parallel to these things. They could run concurrently. When the background thread is done, it goes ahead and completes the future with the result of the multiplication. And that will then allow the join method to return if it's blocked already. Of course, if it hasn't even been called yet, when join is called, it'll return right away. And when join returns, whether it had to block or not, then we go ahead and convert the result to a mixed fraction. So very straightforward. I think you'll agree with me that this looks pretty much like programming with good old-fashioned futures. So clearly, this isn't the reason why we have completable futures. It's just to mimic futures. The problems with the simple basic features of completable future are all the same as we saw before with good old vanilla classic Java futures. You can't chain things together fluently. You can't trigger these things reactively. And you can't handle a collection of futures using just this limited simple interface. And we still have the problem where join will block until the future is completed. And so we all know that these blocking calls can be problematic because the use of blocking in user code and client code and user interface code will underutilize the cores, increase overhead, and potentially block for too long. So it's almost always a bad thing to do. And you just need to avoid using timeouts with completable futures. It's just asking for trouble. So clearly we need something better. We need to leverage the advanced features of completable futures. And that's what we're going to talk about next.